Okay, what we're going to do today. Okay, what we're going to do today, we're going to do standing waves today. Today, we do standing waves in a tube. Oh, let me start sharing the screen, right? Here you go. We're going to do standing waves in a tube, okay? So, we will start, right? We will start with standing waves in a tube. So that's what it is, 17.7. That's section 17.7. -7 in the book. So we did standing waves in a string. Okay, we did that before. And just be reminded, for a standing wave in a string, what do you have for a standing wave in a string? We have a wave propagating in the forward direction, summed up with a wave propagating in the backward direction. Strictly speaking, we must have a negative sign here because the reflected wave gets its amplitude inverted. Okay, so and you know what we got? We had to use, we end up using that interesting relationship, right, for the sign that can be proved, you know, sine of a wave of A plus sine of B. Oh, let's get this one. Okay. One more. Let's wait a little bit, all right? Since there are lots of people coming. Go. Wow. Underneath, you go. Yeah, here you go. Sine of A plus sine of B, right? You know, that's a very easy relationship to memorize. Sine of A plus sine of B is going to be 2 times cosine of A minus B divided by 2, by the way. Oh, no. It's a mixture of sines with cosine. Here you go, A plus B. Okay. Okay, this one here can be here written as, plus with a minus here, right? And then all you gotta do is to apply this relationship to this one here, right? So here go. We're gonna make, this is going to be A. This is going to be B. Okay, good. This is going to be B, right? A, that's B here. That's B. This one sums up. Subtract. And we have another one here, A and A. And then you go ahead, you Kx is doubled. The Vt is canceled. The Vt is canceled. Kx is canceled. And the Vt is doubled. Right? We have 2 kVt with a negative sign in there. 2 kVt with a negative sign. Here you go. The 2 cancel with the 2. And then we get the 2 again canceling out. Because of the negative sign, we can put the negative sign outside, okay? Something like that. And then here go, what we end up having? We end up having an amplitude that varies as time goes by. Okay. And let's see here, someone else. And if you have the other case, right? The other case with a plus sign here is all the way around. If you have something like that, we end up having, a final result like that. Okay, so amplitude here changes as time goes by. Now we have, that's for longitudinal waves. This is the result for longitudinal waves. Longitudinal waves. We have something similar. And what else can you, in the case of these waves, okay, with having 2 ends, 2 fixed ends, having 2 fixed ends, like the string of a guitar, Okay. The boundary conditions, we call it the boundary conditions, okay, can be written as the following. Here you go. Let me see if I can get that. Yeah, I'll get this one here. Yeah. the boundary conditions. So the function of x minus vt, right, is going to be 0 for, and let's see, this is the result. In the case of these waves having two fixed ends, okay, and the string being, and the string being of length L, okay, the boundary conditions is going to be something like that, for x equal to 0 and x equal to L. It would apply to both plus and minus. Okay, for a standing wave, for standing waves, for longitudinal standing waves, we have something similar. But the boundary condition is going to be, but the boundary conditions is going to depend but the boundary condition is going to vary somewhat. The boundary conditions is going to vary somewhat. Similar, comma. The best way is to illustrate those possible cases, okay? So remember, we are talking about not any type of longitudinal waves, right? We're talking about the sound wave. So let's think in terms of musical instruments that we have out there. Let us think in terms of musical instruments we have out there. Okay, we start with the case of a tube with two open ends. One more. See here. Okay, thank you. Okay, so here you go. We have the case of a tube with open ends, okay? Picture all those particles, all those air particles right here in this tube, within this tube. And at the open ends of this tube, the particles can oscillate past this boundary, right? Can oscillate past this boundary here too, right? Can oscillate past this boundary. So what does it mean? Okay, it means that you can have a larger amplitude here and a larger amplitude here. You can have crests here. This type of condition we illustrate more easily as the analogous of a transversal wave. Let me show you how you do that, right? So here you go. So here you go. Do you remember how we illustrate transversal waves, right? So we can do the same here for longitudinal waves because it's very easy to visualize that under those conditions. So here you go. Let's see if I can get it. Yeah. Okay, and then we're going to, here you go. That would be, notice that I am illustrating a longitudinal wave in terms of a longitudinal standing wave in terms of a transverse standing wave, right? Here is like the node, right? Of a standing wave, It's easier to know. And then you can have this end here oscillating back and forth, right? So here you go. Let's see how you can do that. The next one is going to be like that. And then I'm going to adjust the boundaries of this guy. So here you go, like that. And like this way. Okay, like that. We always have constructive interference here and destructive interference here with a node right here at this spot. That's one possible mode that we are going to get. Okay. And let's see here. Let me see if I have a better illustration for that. Interference standing wave. Let's see. Standing wave. Okay, here is a simulation, right? That I got for a standing wave. That's an open tube. You can see that's an open tube because you have S here equal 0.4. Let's see here. Let's go. Let's try the simulation. Let's see. No, that doesn't look like a standing wave. The standing wave. This one here. Yeah, that's definitely not a standing wave. Yeah, even though it's written standing wave here. Let's see if I have another one that's not. Sound. Wait. Yeah, doesn't look like I have one. I have a standing wave for this case. Okay, so here you go. So that would be one possible mode of vibration. Okay. That's for open ends tube. And then you can fit other types of waves as well. Just like you can fit different types of waves for the string. But don't forget, the boundary conditions for longitudinal waves is more flexible than the boundary conditions for transverse wave in a fixed string. You have this one with open ends, okay? And then you can fit another wave in there, okay? So which other wave can we fit? We can fit one with that looks somewhat like that. Here you go. Here you go. One. Let's see if I can get that. One and two. Here you go. Here you go. One more. Sometimes it's easier just to do the drawing by hand, you know, and here you go. Don't forget the boundary conditions. Expect that you have a maximum amplitude. No, that's not. Let's see here. Maximum amplitude. Yeah, I gotta extend that a little bit more, right? Let's extend this a little bit more. Extend it a little bit more. This will be the next. Yeah, that's too big. The wavelength here is too big. Here we go. One more coming. Okay. And let me stretch this one. I'm gonna make a little bit compressed. Let's see. Yeah. Okay, and then we must have another one, just like this, fitting on this end. Okay, it fit well, right? Worked well. Here you go. This one. So just a matter of fitting the proper standing wave within this tube. With open ends, you are going to have, that's the second mode. That's the second mode of vibration. Okay? With open ends, you're going to have maximum amplitude at the edges of the tube. Okay? Okay, that's well, I have the illustration here in my notes, so I don't have to keep on drawing it all over again. Okay, so here you go. That's the first mode of vibration, right? This is a sine wave that two sine waves, right? One upside down, the other upright, with the crests at the edges of the tube, open end tube. That's the first mode of vibration. The next one looks just like that, okay? That's what we have here is a half wavelength. what you have here is a full wavelength. And then you have another one, another mode of vibration. Here you go, 1 wavelength and a half, right? And so on. And now we can start look for mathematical patterns in those waves. Let's look at that. So I'm gonna put it aside. Is a half wavelength without a length of the tube, within the length of the tube, right? So here you go. Let's go, here you go, this one right here. 1/4 of the wavelength, 1/2 of a wavelength, equal to L. Okay, so here you go. Let's write that down. Okay, for the fundamental, have out there. Let us consider first a tube with 2 open ends. Okay, in this case, the boundary conditions states that we have maximum amplitude at the edges of the tube. Okay, so it's going to be something like that. It's going to be 2a for x equal to 0 and x equal to L. Okay. For the fundamental mode, you know, n equal to 1, we should expect the wavelengths to be twice the length of the tube, right? Because we're fitting half of a wavelength. So specifically speaking, we say that wavelengths divided by 2 is going to be equal to L. Okay. Then let's call this one here the lambda, the fundamental mode that I call lambda 1. Okay. For the next mode, we call it mode of vibration. For the next mode of vibration, n equal to 2. Okay. We expect the wavelengths to be equal to the length of the tube. So it's going to be something like that. We can even come and say, you know, 2 lambda 2 over 2 is going to be equal to L. Make sense? Right? So let's take a look again at the drawings. Okay, so here you go. That's 1 lambda divided by 2 is equal to L, right? So here you go. 2 lambda divided by 2 is equal to L, and so on, right? Here you go. 1 lambda and a half equal to L. 1 lambda and a half is 3/2 of a wavelength, okay? 1 lambda and a half, 3/2 of a wavelength equal to L, and so on. Next modes like that. Here you go. 3 lambda 3. Okay. So the way you count is like that, you know? Here you go. 1/2 of wavelengths is equal to L. 1/2, 2/2 of wavelengths is equal to L. 1/2, 2/2, 3/2 of wavelengths is equal to L, and so on. Okay? Open tube, and so on, and so on. So on. Okay, the generic equation becomes, n lambda n divided by 2 is equal to L. Okay, or you can rewrite that as 2L over n equal to lambda n. And then you put a comma here, n equal to 1, 2, 3, 1, 2, 3, okay? Like that. So it's just a matter of making a drawings there and make sure that the drawings fit the tube with the proper boundary condition, right? And we can even also write this equation in terms of the frequency or wavelengths, right? Remember, rewriting the above in terms of the frequency and speed, we get, right? Recall that for the most generic equation for the velocity, lambda n times the frequency is equal to the speed of the sound. Okay, the speed of the sound depends on the medium only. Okay, here write in terms of the frequency, we get, F. You go. You don't need that. Like that. Or even better, Yeah, let's keep it this way. Let's see, there's a better way of doing that. Let's change it this way here. F and lambda. The same equation. And I'll substitute this lambda right in here. To L over n, right? Becomes n here at the top over 2L. Okay, that's another way of writing the modes of vibration. Here we wrote the mode of vibration in terms of the wavelengths. Here we wrote the mode of vibration in terms of the frequency. So it goes with n, directly proportional to n. Okay, that's a two open ends tube. And then we also have the case of a tube that has one open end and a closed end. Okay. Two cases, right? Let's consider first a tube with two open ends. Here you go. Two cases of standing longitudinal waves. Open ends, tube with open ends, and tube with a single closed, with a single open end. Open end and closed end, okay? Two open ends, we're doing two open ends first. Here you go. And now you go ahead and you do the same drawings that we got before, okay? So here you go. That's here you go, is the case of a tube with a closed end and an open end. Because we have an open end here, the particles, the sound particles can oscillate back and forth, right? Across this boundary that we don't have, kind of boundary that you don't have. But here, the particle cannot oscillate at all. It has to be at rest. It shouldn't oscillate here at all. Everywhere else, the particles would be oscillating with a larger amplitude here, smaller amplitude, until the amplitude is zero. Becomes zero right here. So that's the first mode of oscillation that we have for this longitudinal wave. This thing what you see here is a quarter of a wavelength, okay? This is a quarter of a wavelength. That's a half of a wavelength, and then that's a full wavelength, right? So here you go. For this specific case, we can write that down. 1 wavelength divided by 4 is equal to L, okay? So, referring to the drawings, for 1 closed end and the other open end, we have the following. And by the way, we can, don't forget to write down the boundary conditions as well, right? For this case, the boundary conditions. Let's see here, that would be, let's move it aside. Yeah, it's better, you know, instead of writing down in that way that I was, it's better to write down in this way, you know. Here you go. For the open end. What about the boundary conditions for the 1 closed end? For 1 closed end, we have boundary conditions. Here you go. Equal for X equal to L, and here you go. For X equal to 0. Okay, boundary conditions like that. So what do we discover? We discovered from analysis. I'm going to copy all the stuff here. Okay, here you go. Is 1 wavelength divided by 4 is equal to L. Okay, for the fundamental mode, we have mode n equal to 1. Okay, for the next mode of vibration, let's take a look for the next mode of vibration. Okay, so 1/4 of a wavelength, 2/4 of a wavelength, 3/4 of a wavelength is equal to L. Okay, that's how you count. You make the drawings, make sure that you have a maximum amplitude at the open end, make sure you have a node here at the closed end, and then fit your wavelengths accordingly. Okay, so we have 3/4 of a wavelength equal to L. That would be the next one, 3/4 of a wavelength equal to L. What would be the next? That is going to be 1/4, 2/4, 3/4, 4/4, 5/4. Are you getting the pattern here? You go. Right? And so on. The genetic equation being what? What would be the genetic equation? Genetic equation is going to be, let's see here, is 1, 3, 5, right? So it should be 2n plus 1, right? What comes here is 2n, either 2n plus 1 or 2n plus minus 1, right? Either way works. But if you're going to do 2n plus 1, then the n should start at 0, 1, 2, right? And so on. If you do 2n minus 1, if you do 2n minus 1, then the first n should be 1. The fundamental mode should be 1, okay? Or either equation works. Either equation results in the same, gives you the same result. Okay? Oh, let's not forget put this subscript n here. Subscript n right in here. You know, it's nice about this type of theory. It's nice because it's very simple, right? Let's use this one here, right? So you start at n equal to 1. Okay, continue with the last equation. Continuing with the last relation, we have the wavelengths can be written in terms of L for n-2n minus 1 equal lambda n equal for L over 2n minus 1. Like that. We, just like before, we can here write that in terms of the frequency, right? Let's reuse it. The velocity of the sound remains the same in the tube. Here we go. One more. Okay, we plug the lambda n right in here. That's one way. And we can write the frequency in terms of n and L. 2n minus 1. Oh. Oops. (2n minus 1 divided by 4. Go, and now I can, I still have an L in there, right? Did I do it right? Let's see here. Frequency, let's see here. I plug it, yeah. Yeah, it's gonna be 4L. Like that. Okay. So those are the possible wavelengths that fit in there. You should be able to do that easily, right? The series is very, well, the difficult part is to come up with the the way that you fit the wavelengths in there, right? That's for two open ends. Okay. That's the difficult part. Okay, make sure for two open ends, make sure you have maximum amplitude here. And then you have to somehow fit the nodes in there. Similar, same thing here, right? You go. Let's organize them, you know, in a table. I'm gonna put that in a table for you. Here you go. This one right in here. Organizing everything in a table. I'll put here, you go 1, 2, 3, and 1, and 2, and 3, right? You go. And 1, 2, and 3. Lowercase n. Open end. Open ends. One open and one close end. Okay. Go. Okay, two open ends. This goes n equals 1. Let's shrink it as much as I can. All right, so here we go. I want to keep the same size on both here. Yeah, here you go, same size. So that's the most difficult part. The most difficult part is coming up with this drawing. Once you have the drawing, that's easy to figure out what's going to be the relationship. Okay. And next one. Okay, this one here. And the third one. One more. Let's see how they compare, right? We do those tables to see, hey, how they compare with one another. Two open ends. Open ends like here. Nope, not here. Put it down there. You go. I'm gonna copy everything at once. Here you go. Here you go. N equals to 2. N equals to 3. Let's see if I can shrink it. Yeah. Shrink it. Shrink it. And shrink it. Okay. Here. Can I do better than that? Let's see. Yeah, I did everything. Let's see what one put next line is going to be the equation. Okay. Next line is going to be the equation. I can put the frequency here. That should be close one. Yeah, it should be closed and. One of them is closed and. Here you go. That's for the frequency. I'm going to put the F sub n. And the other one, the wavelength, here you go. Frequency of that. Okay, that's lambda n. Close and pick one more. Right here. Okay. And then you gotta have the two open ends equation. And all those, in all those cases, n equal to 1, 2, 3, so on. N equal to integers right in here. Okay, like that. That's how they compare. Let me see. I put, I put the V here. Let's, here you go, like that. No, even better. I put like that, 2L. Okay, and just put N here to make everything symmetrical. For L, V, right? And I put a parenthesis here. Right? Like that. I want to put for L here. What's n in 1? Oh, I don't need this lambda equal, right? What's n in 1 becomes 2n minus 1. Even better. Here you go. Even better. I'm going to put a 2 here. Okay. This term here is the same as this one, right? And then I'm going to do the same here. Let's see. L 1 over n. Let's do like that. 1 over, 1 divided by n times 2L. Okay. 2 divided by 2n minus 1 times 2L. Like that. What changes is the term here in front. Right? What changes is the term here in front. Let's save that. Okay, I want to make sure that you folks can see the exam that I posted yesterday. Can you see that? I want you to go to Canvas. So that's what we have for this part. Please go to Canvas and check if you can see the exam there. Okay, I posted for everybody that in the list, right? Top of the table. Okay, Jennifer, did you see what you want? Let me see. Jennifer, you asked me to scroll up here. Okay, so I want to hear from everybody, please. And well, let me see. Let me take attendance first, and I will ask while I call your name. Okay. P39 attendance roster. P39 lecture. Today is the 22nd. Toby, are you there, Toby?
Yeah, I'm here.
Okay. Do you see the exam there in Canvas?
Yes.
Yes. Okay. Good. But it's not available yet, right?
No.
It's going to become available at 11:59 a.m. Huh? Harun, do you see the exam there, Harun?
Yeah.
Okay. It's going to become available at 11:59, right? a.m. Musa, do you see the exam there? Yes. Good. Thank you. Zachary? Are you there, Zachary? Yeah, I don't see Zachary here. Elena, are you there? I don't see Elena either. Crystal? No, Crystal, right? What about Brian Spina? I don't see Brian either. Robert Foss, you see that, right, Robert? Okay. Okay, good. Pedro Flores, you see that, right? Yeah, good. Thank you. Lawrence Flores. Let's see if Lawrence is.
Yeah, Prof, I'm here.
You see it?
Yeah, I saw it.
Okay, good.
Thank you.
Awesome. Thank you. Daniel Freire?
Yes, I'm here and I see it.
You say, okay, good. Amalia Gale?
Hi, Professor. Sorry, my mic wasn't working there for a moment. I have the test.
Okay, you see the test. Okay, good. Thank you. Tiffany, Wang?
Yes, I can see the test.
You can see it? Oh, okay, great. I did something slightly different than I used to do before, so I want to make sure that there's no bugs in there. Olivia Kruger? Yes, okay, great. Daniel Yang? Good, thank you, Daniel. Sarina Lobana? Thank you. Anthony Lopez? Yeah. Chuk Tao Lu? I can see. Yes, good. Thank you. David Maes. Is the Dave here? Yeah, I can see him in the list. Hi, Dave. Can you hear me? Okay, I'm gonna put a star here. Ryan McNeil. Yeah, thank you. Alexis Nigret.
Here, I got it.
You got it? Okay, you see the exam. Daniel Nwagbo.
Yeah, I have it.
Good, thank you. David Nwagbo.
Yeah, I have it.
Okay, good. Claire Ottinger.
Yeah, I see it.
Okay, good. Blue. Next is Jennifer Ramirez. Good, thank you. Noah Raymond. Okay, good. George Risk. Okay, hi George. I see you in the list here, but I don't hear you. I'm gonna put a star. Okay, next. Safi.
I'm here and I see the exam.
Thank you. Natalie Santiago.
I can see it, Professor.
Thank you. Nathan Silva. Darnice, Simon. Hello, Darnice. Okay, I'm gonna put here a star. I don't hear you. I don't see anything. Okay, good. Thank you. Okay, so you see, right? Kenny Villagomez.
Hey, Professor, I'm here.
You see it?
Yeah, I saw the test.
Okay, good.
Thanks.
Nolan Williams.
Yeah, I can see the test.
Okay, good. Mengshu Zhang. Mengshu. I see Mengshu. Yes, I can see it. Good. Is there anybody else? So Olivia, right? Are you there, Olivia? Okay. Okay, you cannot see the exam, right, Olivia? Okay, so yeah, I'm gonna, let's have a little break now. I'm gonna call Canvas and let's see if I can resolve that for you, okay? I do not know if I will be able, never have a case like yours. So try to see what they can do there, okay? Okay, so it's 9:05 right now. Let's take a break. Till 9:20 a.m., okay? I'll save that and I'll see you soon. Okay, we are back here. Now, while you are there, please make sure, please take another look at your exam. Okay, I made a small modification in there. I want to make sure everything, again, is in good shape. Everything is right. So make sure that you can access the exam, that you can see the exam just like you saw before, okay? In Canvas, right? And it's 9:20 now. Let's see here. Lawrence is coming. One more. Oh, whoa. Let's see. More people coming. What we are going to do now is a very interesting type of phenomenon that's called beats. Okay, that's section 0.8 in the book, 17-8 in the book. Okay. Okay, so you know what's beats, okay? Beats, whenever you have the superposition of two waves with two waves of, oh, I gotta share the screen, right? Thank you. Here you go, sharing the screen. Beat section 17.8. Whenever you have the superposition of two waves of different frequencies, right? Or wavelengths, right? You get an interesting pattern that can be easily recognized, especially for sound, okay? But remember, this beating phenomenon applies not just to sound, but applies to other types of waves as well, okay? This type of phenomenon applies not just to sound, but to any other wave phenomenon. So what I'm talking about, okay? So far, we have been talking about interfering two different waves, two waves that have the same wavelengths, that have the same frequency, but slightly different phases. Okay, that's what we have been talking about. So here you go. So far, we have been treating waves, the interference of waves of same wavelengths slash frequency, but different phases, okay? Specifically speaking, what we have been doing so far is something like that. Let me get the equation for you. Okay, so here you go. That's the type of interference. Let's see, here you go. I'm gonna get this one here. That's the type of wave. Let's put a plus here because we have been. This minus sign here implies a different phase, okay? We also did, here you go. We also did this other type of interference. Plus 5. What we're going to do today, right now, is going to be different. What you're going to do now is going to be something like that. Let me see here. The first wave, I'm going to put that in the notation of the book, okay? KX. Okay, so here you go. And then, I'm gonna omega. And then that's gonna be omega 1. Okay. That's going to be, go, okay. And there's no phase difference from the beginning. It's going to be omega 2 here. Omega 2. And I can even okay, because we have a different, you know, a different wavelengths, we're gonna have also different case, okay? Don't forget what you have here is 2 pi f, right? 2 pi f as well, but now we have different frequencies, consequently we have different wavelengths as well. But we're going to be observing, we're going to be listening to those waves at a given point, okay? A specific point. We will be listening to these waves at a given position. X1, let's put this one like X1. Go. Okay, so it's gonna be something like that. X1 and X1 as well. The position for both waves are going to be exactly the same. Okay, there will be a slightly phase difference because of those two values here, but we will be listening as time goes by, okay? Phase here. Go. So think what might happen, okay? To make things simpler, you know, I'm gonna make things even simpler. I'm gonna set the origin of my x-axis to my ear, okay? Setting at the given position, setting, here you go. Setting the origin of my x-axis to the position of my ear, okay? Or sound detector, right? That's what a ear is all about. It's a sound detector. We get a simpler relation. You know, we will get like x1 equal to 0, right? It's a simple relation. This thing here becomes 0, right? This one also becomes 0. What I'm going to do, let's see, I'm going to do according to the book. Okay, so instead of a sine wave, I'm going to put a cosine wave here, just to be consistent with the book, okay? Not just with the book, but with my notes as well. Here you go. Go, cosine. Those two waves, we are assuming that they have the same amplitude, okay? Here you go. Here you go. We get this relationship here. Don't forget this omega is a function of the frequency, right? 2 pi f, 2 pi f1, 2 pi f2. Okay, so here you go. We can eliminate the negative sign there because cosine of a minus a is equal to cosine of a. Okay. I'm going now to rewrite that in terms of the frequency, although it's not necessary. I'll do that anyway because the frequency is a quantity that more familiar, right, than the angular frequency. And now we apply that magical relationship again that we had before, right? And this time for the cosine, here you go. Instead of the sine, we're going to apply for the cosine. It's like that. We're going to be using that relationship over and over again. Here you go. Cosine of A plus cosine of B. It's very easy to memorize this relationship. Is going to be given by twice the cosine, okay? And what goes here inside is going to half, and one term is going to be A plus B, the other term is going to be A minus B, right? It's very easy to remember. If it's cosine, you're going to have cosine and cosine here, right? If it's sine, here you go. This is slightly different, but here you go. We have sine and cosine. Okay. If it's sine A plus sine B, you know, you have cosine and sine. If it's sine cosine of A plus cosine of B, you have cosine and cosine. Now, when we apply this relation right here to this, to my previous equation, look what we end up having, right? We are going to end up having twice of A, okay? I'm gonna do, here you go, I'm gonna do like that. Okay. 2 pi f1a is A, right? Pi f1 is A. 2 pi f2t is B. 2 pi f2d is T. Here you go. Like that. And now I can, okay, I don't have this 2 here, but I can factor the A to get something like that. And now I go ahead and replace, okay, what I have here. Let me, yeah, here you go. I'm gonna do like that. Here you go to A. I'm gonna replace it now. Okay, here you go. I'm not done yet. I'm not done yet. What we end up having, I'm going to switch the terms, just like you switch it there in the book. Okay, I'm going to put 2 pi t in evidence. Pi t in evidence, here you go. This one, 2 pi t in evidence on the other side. I'm gonna even, okay, copy and paste it here. We got a sum, and then what do you have here? When we plot this relationship here, okay, here you go. It lends to an important interpretation. What you have here lends to an important interpretation. Here we have a term that has a high frequency. Okay. Here, this f1 plus f2 is always going to be greater than f1 minus f2, right? So here we are going to have a term with a high frequency and another term with a low frequency. Sometimes it's not easy to see that, but if you plot that, it's going to become intuitive, okay? So basically what you have a term with a very high frequency, okay, very high frequency, and another term with a very low frequency. And this low frequency here is modulating the term, modulate the high frequency term. Okay? When you plot that, you get something like that. Let me show you. You get a series of lobes, beats. Not this one. No. Let's see. Not mistake, not this one. Let's see, must be another one. Bear with me. Here we go. Beat. Interesting. That's not what I want. Standing with. Oh, what a shame. Where is my? I have a beat here, but that's not what I want. Interesting. Okay, so let me see if I can plot this one instead. No. I don't have it. Well, I'm gonna show you my own plot, okay? Unfortunately, I don't have that in Excel, but I have here in my notes. Okay, so that's what happens when you plot a graph like that. Okay, we have a term here with a very high frequency. Well, we are plotting here against time. Okay, amplitude versus time. That's the high frequency term. And this other term here is the low frequency modulation. Okay. So if you are hearing that in terms of sound, what you're gonna hear? You're gonna hear something like can you picture that? Okay. So you have an amplitude of the sound that's going to be almost zero here. You increase in intensity, and then decreasing intensity. And this increase and decrease has a frequency that is given by the F1 minus F2. Okay? And I can show you exactly how it looks like. Okay, there is a software out there. Oh yeah, you already been exposed to the software before, right? I showed that to you before, and I'm gonna reuse it again. It's the tone generator software. Remember that? There you go, 440 hertz, right? 440 hertz. Stop it. And now what I'm going to do, I'm going to sum this frequency here with another frequency. I'm going to play them simultaneously. Okay, you can do that in your computer as well. And I'm going to keep the same amplitude. Okay, so here you go. And so you can experience what beating is all about. It's phenomenal. Okay. 440 hertz, 440 hertz here, right? Here you go. They should have the same amplitude. Here you go. I'm gonna put 441. Oh my goodness, I don't need that. 441 hertz is slightly different. Is a different in frequency of 1 hertz. Okay, 1 hertz different in frequency. I'm gonna play this one, and I'm gonna play this one. Do you hear what's happening here? That's what I call beating. That's what we call beating. You have this pulsation in the sign, in the intensity. And the frequency of this pulsation, of this pulse, is exactly 1 hertz, because it's the difference between 440 and 441. 1 hertz is approximately 1 second, okay? I can go ahead and make this pulse, this beating, longer than 1 second. In order to do that, what do I have to do? I have to change the frequency slightly here. I have to make the difference in frequency equal to half of a hertz. When we do that, this spacing, this time difference is going to become 2 seconds, not just 1 second. Do you see that now? Do you hear that? This thing is like 2 seconds, okay? Because we have a half hertz difference between one frequency and the other, and a half hertz difference is 2 seconds, okay? Time interval. I can go even shorter than that. Let's see if I can go 75. I'm gonna go 5 seconds now. Now we have 0.25 hertz of difference. See that? You can time it in your clock. 0.25 hertz of difference. 0.25 hertz of difference is what? 4 seconds, right? 4 seconds. We can even time it. Let's see, let's time that in the clock. We're gonna start the timer at 0 amplitude. Here. Here, I'm getting 3. Yeah, 3.95, almost 4 seconds. You can do the same. I'm getting 3.95, which is almost 4 seconds, right? There is a reaction time difference here. And I can go even longer than that. If I am patient enough to time it, I can make it 0.1 hertz difference, and you're gonna have a 10-second difference in the beating. Okay, here you go. I'm gonna time it again. I'm gonna wait for the sound to become minimal, right? Here you go, I started. Yeah, I got 10 seconds, 10.01 seconds. You can do the same. You can go even further than that, right? You wanna do, let's say, 20 seconds? Period of 20 seconds, here you go. 20 seconds period should be 0.05 hertz, right? So here you go. Play. This one is gonna last longer. This type of effect is very important. Here you go. Wait until it becomes almost. Here you go. Start right now. Wait until the sound fades away. I'm not even looking at my watch. I'm just paying attention to the intensity of the sound. When it becomes 0, I'll stop my watch. Here you go. I got it. I got 19.75 seconds. Okay? Very close to 20 seconds. Don't forget there is some reaction time difference in there. But you get the best results when you have the least frequency difference. In this case, is 0.05. Did you get the idea of the what beating is all about? Stop this one. I'm going to stop this one. Okay. And here you go. Now let me see if I have. I want something. Okay. So here, where you had the intensity of the sound that was very low. Notice that this period that we are talking about is very long, right? It's more than 200 seconds. That's because I used a frequency that is very close to each other. Let me see if I wrote. Yeah, I didn't say what's the frequency that I used here. Okay, frequency difference that I used here. But you can go into Excel and come up with this graph. Let me see if I can find it. I thought I had this graph in Excel. Let me see here. Sound. No, we have just waves. Unfortunately, I don't have the beating. At least I'm not finding it. Interference. Okay, the beating that I have is in the 2-dimensional. Yeah, see that? It's not, I didn't plot against time. It's just a matter of that's not what I want. Not this one because relativistic. Let's see here. Let's see. Nolan, yeah. Let's see, P39. Attendance. Let's see this one. Maybe it's in another spreadsheet of mine. Let me see if I can find it. Young double slit oscillation, maybe it's here. No, it's not here. Well, if I were to plot that graph for you, I have to go from scratch. I don't want to do that, okay? Don't want to do that. But that's what this phenomenon is all about. Okay? The beating frequency. Here you go. Let's go back to the. Here you go. The beating frequency is let's say the frequency F1 minus F2. The frequency. I'm going to even put that in magnitude. Okay. Is lower than the other frequency, right? This smaller frequency is called the beating frequency. Or, you go. And it modulates the intensity of the higher frequency wave. Because these two frequencies are very different, okay? Because these two frequencies are very different, we can easily perceive the modulation of the lower frequency. Well, it's not that we can easily perceive, okay? It all depends on the beating frequency, right? If the beat frequency is very small, then you can perceive. But if the beating frequency is not very small, then it becomes kind of hard to perceive. Let me tell you what I mean about that. Suppose that I have 441, 440 here, right? And 441 there, right? Here you go, I'm gonna play that. That's 1 second, right? But then as the frequency difference becomes larger and larger, see the beating becomes faster and faster, right? It comes to a point you can no longer perceive the beating because it's so fast. See, that's 1/3 of a second that we have right now. That should be 1/4 of a second. Hear that? 444 hertz, 440 hertz. It's easier to time this frequency whenever the two frequencies are very close to one another. Here is the next one is going to be 5 hertz of a difference. Okay? Eventually, when the difference is so large, it becomes rather difficult to perceive the beating. Oh, hear that? That's 10 beats per second. What you have here, 10 hertz of a difference is 10 beats per second. Let's put 20 beats per second. Here you go. You hear that? right? And if I exaggerate, if I go to 500, here you go. Now we're talking about what? 60 beats per second. Comes to a point that the ear cannot perceive the beat anymore because it's so fast, right? If I put 400, let's see, 440, let's put 100 beats per second, okay? That's 100 beats per second, okay? So I cannot say easily perceived. It all depends on the beating frequency. Very different. You can perceive the modulation of the lower frequency. Okay, by the way, the smaller the beat frequency, the easier we can perceive it. Okay? So for a beat frequency of 1 hertz, for a beating frequency of 1 hertz, we can hear pulses of 1 second duration, right? For a beating frequency of 2.5 hertz, you go, we can hear pulses of 2 seconds of the duration. Okay? For a beating frequency of 0.25 hertz, what do we mean? A difference in frequency, right? Of 0.25 hertz, we can hear pulses of not that last, not, let's see. Yeah, we can hear pulses separated, you know? Separated by, we can hear pulses separated by 1 second. That would be a better way, separated by 1 second. It's not that the pulse has 1 second of duration. No, 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 because they are separated. Pulses separated by 2 seconds and so on. Separated by pulses separated by 4 seconds and so on. And so on, okay? So problems like that that you're gonna see is, you know, you have to determine what would be the beating frequency. 9:54 right now, we still have time, right? Still have plenty of time here. So let's go through again the exam again, right? I want to make sure I made some changes there right now during the first break, and I want to make sure everything still remains the same, that you still can access, okay? So I'm going to go through the roster again. Toby, can you still see the R exam there in Canvas? Is Toby there? Let me see. Toby. Toby must be away from his computer. I'm gonna put a question mark here. Harun, can you still see our exam there, Harun?
Yeah.
Okay, good. Musa, can you still see the exam there? Yes? Okay, good. Next, Zachary. Zachary, can you see your exam there, Zachary? Zachary is not listed here. Yeah, he didn't come. Let's see. Elena, is Elena there? No, Elena is not here. Crystal, Luis Crystal, are you there, Crystal? No. Brian Spino. I don't see Brian there. Robert Falls, do you still see your exam there, Brian, Robert? Good, great. Okay, so it looks like the modification that I didn't mess up with the stuff there, right? Pedro, do you see your exam there? Do you still see your exam there, Pedro? Yes, good, thank you. Lawrence, Do you still see your exam there, Lawrence?
Yeah, Prof, I see it.
Okay, good, thank you. Danielle Freddy? Is Danielle there?
It's loading. I'll let you
Oh.
know.
Oh man, it takes some longer.
It's the thunderstorm that are messing up the internet connection.
Uh-huh. Okay, while you load, let me know. Okay, well, once you load, you tell me. Okay. Let me go to Amalia. Amalia, do you still see your exam there?
I still see my exam, Professor.
Good, good. If there must have been a slight change for you, for some of you, not for everybody. Okay. Tiffany, do you still see your exam there? Yes, thank you. So Olivia Kruger.
Yeah, I still see it.
Good. Oh, great. Danielle Liang. Danielle Liang. Hi, Danielle. I don't hear from you. Let's go to the next one. Sarina, do you still see our exam there? Sarina, can't hear you. Next. Anthony Lopez. Yes, good. Chuck Lu. Do you still see your exam? Good. Next, Dave Maes. Are you there, Dave? Yeah, Dave. Now he's not even listed here. Okay. I'm gonna put Ryan McNeil. Do you still see your exam there? Good, thank you, Ryan. Alexis Nigret. Alexis just came on board. Are you there, Alexis? Can you hear me?
Yeah, I got it.
Do you see your exam?
Yes, sir.
Okay, thank you. Daniel Nwabo.
Yeah, I have it.
Okay, good. Dave, Daniel and Dave Nwabo, do you see your
Good,
exam there?
good.
Good. Claire Ottinger. Are you there, Claire? Okay, we are coming very low. Okay, I heard you. Jennifer, can you see that, your exam? Jennifer Ramirez. Let's see, Jennifer Ramirez. Okay, I can't hear you, Jennifer. Noah Raymond. Good, great. George Risk. Can you see your exam there, George? George, I can't hear you, George. Jennifer Ramirez. Okay, thank you, Jennifer. Safi.
Yes, I see the exam.
Thank you. Natalie Santiago.
Yes, I can see it.
That's great. Nathan Silva. Good. Darnis. Are you there, Darnis? Okay, put a question mark here. Kenny Villagomez.
Yeah, Professor, I see it.
Okay, great. Nolan Williams.
Yeah, I still see it.
Okay, and Meng Shu.
Yep, I still see it.
Okay, good. So there's no problem here. Okay. Yeah, Olivia, I called, we can talk about that before the exam, okay? But I called Canvas, then I also called a counselor, she still didn't reply back. I couldn't talk to her. So let's see what happens, right? But hopefully you can resolve your problem. And so we're all in good shape here. 10 o'clock right now. Okay, what we're going to do now is the Doppler effect. Doppler effect. Here you go. Doppler effect. So let's just summarize what we have done so far. Okay. Propagation of a single wave, right? Propagation of a single wave. Then we start to talk about interference of waves. Most of this chapter is in terms of interference of waves, right? We look at interference between two waves of different phases, right? And when we did that, standing wave is just an interference of two waves of different phases. But we also look at the interference of two waves of different frequencies. Two waves of different frequencies. That's where we get the beating. And now we're going to look at the Doppler effect. Okay, what's the Doppler effect? Doppler effect is a phenomenon related to what? Relative velocity between a source and a detector. Okay, that's what Doppler effect is all about. So if you are, if you are at rest, if you have a source of sound, a sound source emitting it doesn't have to be a sound source, okay? If you have a source emitting a wave, okay? Emitting a wave of frequency F, okay? An observer at rest with respect to the source will measure the same frequency F for this wave. However, if there is relative motion between the source and the observer, the frequency, the measured frequency will be different. Will be different, okay? That's what the Doppler effect is all about. We're going to get into the details of this phenomenon. Okay, so here you go. Let me get, here you go. Consider a point source emitting a wave. This is a spherical wave. The wave is propagating away from the source. And it has this wavelength lambda, right? Remember I told you how we represent a wave? What you see here are the crests of the wave. Crest, crest, and crest. Somewhere here in between you have the valley, right? And right here we have a node, right? Let me, no. Yeah, I cannot change it. I'm not gonna change it. But can you picture that, right? Dashed lines represent a valley. Dashed lines here represent a valley. Dashed lines represent a valley. and just a single dot here represent the node, another single dot here represents a node, right? Two nodes between the crests of the wave. Okay, so if you have here an observer, okay, he is going to measure wavelength lambda. Okay. Now, what if the observer starts to move towards the source of the wave? Okay. What he starts to move towards the source of the wave? If you start to move towards the source of the wave, there will be, a new period for this wave. The wavelength is going to remain the same, right? But what about the period? Let's do the math here for you to understand. Here you go. We have that relationship, okay? For an observer at rest with respect to the source of a wave, we have, is equal to lambda divided by t, or t is the period, right? Here's the velocity of the wave, the wavelength of the wave, and the period of the wave. The observer is going to measure a period t. The wavelength can be measured, let's say, with a drone, right? That can image the waves of an ocean, for instance, right? Or you can even put a very long buoy that has a given length, and that buoy has a ruler, and then you can measure the wavelength as well of the wave, a given instant of time. But what if the observer start to move? For an observer that moves towards the source with velocity v naught, we have a different relation now. Now the relative velocity of the wave is going to be v, the velocity of the wave, plus the velocity of the observer, right? And we are going to end up having a different period for this wave. The period here in this case for the observer at rest would be lambda divided by v. But for the observer that's moving, it's going to be a shorter period. That applies not just to regular waves in the sea, right? Water waves, but also applies to sound waves as well. Okay? So in this case, period measured or perceived, right? Measured or perceived period of the wave decreases. What does it mean about frequency? Which means that the frequency increases, right? Or And I even gonna, you go, put the equation for the frequency here. Here you go. Frequency is V over lambda for the observer at rest. Oops. Go. Frequency. I'm gonna put it here. Now the new frequency, right? I'm gonna put F prime. I'm gonna put that T prime, right? Because now the source is moving. So the wavelength remains the same, but the frequency changes because the velocity, the relative velocity changes, the perceived frequency. Okay? So we can here write the new frequency in terms of the old frequency. Here writing the new frequency in terms of the old frequency. What frequency means observer frequency, observer at rest. Whenever the observer is at rest, we have, right? V over F, right? And we can go the next step here. Here you go. F gets here. We can here write that. Okay. 1 plus V naught divided by V. Okay. So the new frequency is greater because we're moving towards the source. What if we're moving away from the source? What if we are moving away from the source, right? Well, all you have to do is to change the sign right in here. Okay, the relative velocity. See, I don't have a drawing for that. The relative velocity becomes less, not more. Okay. The relative velocity becomes less, not more, right? Or we're gonna get something like that. Here you go. So frequency decreases. Frequency decreases, right? So I like to say here, I like to say something like that. You know, in the first case, towards, right? Moving towards. The frequency is greater than the original frequency. Moving away from the source. Moving away from the source, frequency is less than the original frequency. Okay. This here, this shift that we see in the frequency, this shift in the frequency, we call this frequency, this shift towards higher frequencies, we call blue shift. Okay. This shift towards lower frequency we call red shift. Why blue and red shift? Okay. Blue and red shift is because of the analogy of the electromagnetic spectrum. Okay, because of the analogy of the electromagnetic spectrum. Red wavelengths. Red light, you know, red light has a lower frequency than blue light. Shorter wavelengths. Shorter wavelengths has a lower frequency. Longer wavelengths. That's the analogy of the electromagnetic spectrum. So that's what you have to know. Moving away, lower frequency. Moving towards higher frequency. That's the case of the source of rest. This is the case rest and a moving observer. Okay. So that's the case also of the ambulance coming towards you, right? You hear, not only you hear that the noise is the sound is increasing in intensity, but also the frequency of the sound is higher. When the ambulance passed by you with the siren on, then not only you perceive that the sound, the intensity of the sound is decreasing, but also the frequency is going towards lower frequency. Okay. So now that's the case. What about the case of a moving source? What about the case of a moving source? We did for source at rest, right? But what if the source is moving and you are at rest? Moving source and you are at rest. Okay. See if I have it here. Yeah, unfortunately, I do not have an illustration here for that. But maybe I have it here. Moving source. Moving source. Okay, here we go. Yeah, I have a simulation here for you. So let's start at time t equal to 0, right? Here's the source. My source, your ambulance is moving, right? Your ambulance is moving towards you, is emitting a sound wave. Okay. Notice that the source here is moving, right? Here you go. Just initially at the origin and now is a little bit to the right. Okay. X is what? X is, let's see, C2. Yeah, X is the position of the cosine of B. Let's see. Yeah, X must be the position of the, yeah, is the position of the source. Let's see here. Oh no, here you go, right in here. At time t equal to 0, here you go, X, the position of the source, okay? Time t equal to 0. At time t equal to 1 second, the source moves a little bit to the right, okay? And not only the source moves a little bit to the right, but the crest of the wave is expanding away from the initial position, okay? What about the 2 seconds later on? Here you go, it's expanding. Notice that the center of the wave is still at the origin because it was originally emitted right here at the origin. Let's see, at 3 seconds. No, right in here. Here you go. The source is moving to the right and the wave is expanding. Okay, here you go. 4 seconds, 5 seconds, 6 seconds. Eventually, it's going to move, it's going to emit another wave. Let's see when it's going to do that. 8 seconds. No, it didn't do that yet. Let's see. Do I have it here or not? Maybe it's not the simulation. Let's see. 200. Nope. 20. Oh, yeah. Okay. Okay, so let's continue here. Eventually, we're going to see the. Okay, around the 10 seconds, the second wave is emitted. Okay? And now, look at the interesting thing here. In the direction of motion of the observer, the wavelength is shorter. See that? In the wake of the source, the wavelength is longer. Make sense? With this simple explanation, we can see something like that. Let's see, 21 seconds. Oh yeah, here you go. Around 20 seconds, we meet another wave. Okay, so the period of this wave is around 20 seconds. 21, let's see here, G. Yeah. Okay. So now we can, from this drawing alone, we can find out what's going to be the wavelengths. In the previous case, the frequency changed. In this case, it is the wavelengths that's changed. The wavelengths around the source. We have a shorter wavelength in front of the source, and you have a longer wavelength in the wake or in the back of the source. Okay? And then we have our observer somewhere around here. Let's see what's going to be the wavelengths. Just by analyzing this figure, we can figure out what's going to be the wavelengths measured by the observer. This wavelength is lambda prime. Okay. In front of the source, this is the case of source right now. What about the, okay, here you go. For a moving source, the wavelength is shorter in front of the source and longer behind it. We say that the moving source compresses the wavelengths in front of it. Okay. So, in front of the source, we have lambda prime is going to be, I'm going to say this our original wavelength whenever the source is at rest, minus a delta lambda. Minus a delta lambda. Okay? The question now is figure out what this lambda is. Okay. Mhm. Okay, so here go. Look at that. So what we end up having here is the following, the wavelengths. Take a look at the drawing, right? Here's my new lambda prime. So what we are going to have, we have this distance here travel. Let's go back a little bit to 10. 10.5, right? Let's see, here you go. Yeah, when the source is about to emit the wave, yeah, the source is emitting this wave at 10 seconds exactly, it's just like that we don't see it, 10.001. Let's see if we can get, yeah, see that is at 10 seconds. That's the period of this wave itself. That's the period of the wave itself. Mm-hmm. Here's my lambda prime. Okay, lambda is going to be longer than lambda prime. Okay? And it's going to be dependent on the speed of the source. Okay, what this distance here is what is Vs times the period, right? Vs times the period. So what we can say, what we can do is to state that the new lambda, oh, did I put it? Yeah, I'm supposed to be, put equal here, sorry, okay? What we can state is that this new wavelength is going to be the velocity of the source. Okay, good. Time the period of the source itself. Okay, which can be rewritten as velocity of the source divided by the frequency of the wave. Let's rewrite that in terms of the frequency. Okay, so here we go. Now, what we have here, we're going to have 1 divided by the new frequency, right? 1 divided by the old frequency. Wait a minute, it should be a V here. Yeah, lambda F is V, right? Here you go. Velocity of the wave. Let's see here, let's see if I did it right. Frequency, okay, now I have to invert it. Let's invert it. That's gonna be F prime divided by V, right? Oh, I'm gonna go one more step here. Let's do one more step here. V minus V of the source. Yeah, one more step here. And now we can invert it more easily. There's going to be F of V minus Vs. Okay. And here we go. We're gonna, put a P right in here. F prime. Can you do better than that? Yeah, we can do better than that. We can switch the V with F. The V with F here. Note, see that this term is greater than 1, right? Consequently, the frequency is going to be higher. The new frequency is going to be higher. If the source, that's for a source, that is for a source moving towards an observer, right? What if the source is moving away? So all you gotta do is to change the sign right here. And you're going to have the inverse. Lower frequency. Okay. Okay. By the way, this is assuming that V sub S is less than V. If the V of the source is greater, then we have another phenomenon, an interesting phenomenon that I'm going to talk about shortly. It's 10:35 right now. Any questions about that? Let me pause the recording. Okay, I'm back here. Just quickly review what we did here for that equation, okay? Maybe it was not clear to some of you how I got that equation for the new wavelengths. Let's go back to the equation. Here you go. The new wavelengths is right in here, right? And how do I get the next equation? How do I get this equation? How do I get this one, right? You have to refer back to the drawing that I made it here. Remember that this wave was this wave that you see here, this wave front that was initially here was emitted whenever the source was at rest, right?
Professor, you're not sharing.
Oh, thank you. Thank you. Thank you. Here you go. So remember that here you go. This wave here was emitted at this point in space, right? And the source moved from here to here. At this instant of time, you know, the distance from here to here is that equal to the period of the wave. This source here is about to emit a second wave front, So from here to here is going to be, the amount of time from here to here is going to be the period of the wave, okay? And now that the source is about to emit the next wave front, the observer that is right here, laying right here along the x-axis, is seeing this wavelength lambda prime. because we have a period of a wavelength, lambda is this whole distance right in here, right? From here to here is gonna be lambda. Right in here, it's not lambda because the amount of time that went by from here to here was less than the period. But when the source have moved a distance equivalent to a single period, then that's going to be the wavelength, the regular wavelength, lambda. From here to here is lambda, from here to here is lambda prime, and from here to here is the velocity of the source times the period. So that's where I'm getting that equation, okay? Lambda prime, no, sorry, lambda prime is equal plus VST is equal to lambda. Okay, that's how I'm getting that. Maybe I will just copy that and paste there in my, I'm gonna paste right in here. So let's see here. Pasting right in here and, oops. What's going on here? Okay. So I'm going to instant of time t, instant of time t equal to the period of the wave, okay? To the period of wave. I'm going to get this distance, distance from here to here is going to be lambda prime. Make it thicker. And what else I'm gonna do? No, that's not what I want. I want the other one. Format shape. Go. This one, okay? That's gonna be lambda prime. That's obvious, that's understandable to you all, right? Here you go. And I'm gonna get as seen by the observer symbol. Here you go. From here to here, the distance is going to be the velocity of the source times the period of the wave, because this source is about to emit a second wave. This distance here and right in here. Oh, wait a minute. Okay, right in here. Oh, shorten it a little bit. Okay. And the distance from here to here is lambda. I'm gonna copy that. These are full wavelengths. That's how I get that equation. I don't need that, right? And what's that? I don't need that either. Admit, here you go. Okay, so that's where it comes from. And here's for the other one is the same thing. Doppler effect. Okay, that's what the Doppler effect is all about. And now the last thing that we're going to do is supersonic speeds and shock waves. Okay, so here we go. This one is gonna come right here. Okay, and I have a nice illustration for that as well, simulation for that as well. Let's see here. Moving source, standing wave, relativistic Doppler. This one may be. Source velocity. The velocity source. And 0.5. Okay, let's see here. Let's put 1 here. And let's see if we can get that going here. Yeah, here you go. I'm going to start at time t equal to 0. Okay, here you go. Here is my source. Now we have a source here that's moving at the speed of the wave. Okay? It's not hypersonic yet, but it's moving at the speed of the wave. This value here is the speed of the wave 1. Okay, so let's go. Here you go, 1. Here you go. You see that the source is moving at the speed of the wave is right there at the edge of the wave, right? The case of, for instance, of an airplane that's flying at the speed of the sound. Then something happened at whenever t is equal to the period of the wave. The period of the wave is 10 seconds. At this very moment, the airplane is emitting a second wave. Let's take a look what happened. 11 seconds. Hey, wait a minute. No. I gotta do something else here. Okay, so let's see. I gotta readjust my, maybe. Oh my goodness. Yeah, I didn't adjust it for the supersonic speed here. Let me see if I can get it. Maybe it is somewhere else. Okay, now. Okay, must be here. Okay, that's the one. Was looking at the wrong one. Here you go. Now let's see, source. Time t equal to 0. Let's go time t equal to 0 here. Right. And the source is moving at the speed 1.5 the speed of the sound. So let's run the simulation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? See, the source is flying faster than the sound itself. Okay, and now it's emitting the second wave. See that? Okay, 11, 12, 13, 14, 15, and so on, okay? So here we are doing at 1.5. Let me see if I have to change anything else here. Let's do at 1 instead. I wonder, let's see, this guy should be here. That's the second wave. 15 Emma, 15 Theta. Well, we're gonna keep it at 1.5. I don't remember how to change that anymore. Let's see, relativistic, no, that relativistic Doppler doesn't apply to that. Okay. Y source is at 0. Y is 15, M2. Yeah. Yeah. Okay. So let's keep it like that. I cannot figure out how to. You might 5. Is that the reason? Must be this why. Let me change a little bit here. I'm gonna put 1 here, and instead 1 here. I'm gonna put 10. Let's see if it works. Doesn't work. I go back. Yeah, and then if I put 10 here, I must put 10 on the others as well, right? Yeah, it's not working well. Okay, so let's see if it works now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see, we should have the second wave coming out. Yeah, okay, good. Yeah, it's working now. 14, 15, okay, here you go, 16, okay. So see what's happening here when we have a source moving at the speed of the wave itself. The wave can be the sound as well, okay. Let's see, yeah, this 21 needs to be changed as well. It's already changed. Should be 20. Yeah, should be 20. Yeah, okay, good. So I'm supposed to change that, right? Here the third wave coming in. Now we have it right. For supersonic speeds. I need to make it, so let's go, here you go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here you go. This next wave is coming right now. At 11, you start to see the next wave. See that? Now, notice what happened when the source moves at the speed of the sound. Something interesting happens. The principle is exactly the same as before, right? Here you go, 20. Now we're gonna come up and see this next wave. So do you see what's happening here? The wave front is interfering constructively at the same place, okay? So what's happening? You have here a region of high pressure, another region of high pressure, and a third region of high pressure. And all those three regions of high pressure are interfering constructively around this region, creating a region of even higher pressure. Okay? That's where we have a louder sound right here in front of the airplane. Right here in front of the airplane, you have a very loud sound. You don't have those things at supersonic speeds. You don't have those things. If I change the speed here for you, here you go. Instead of 1, right, Mach 1, I had like Mach 0.6, for instance. And I have to change that here as well. Right, here you go. I have to change here to 6. And I have to change this one to 12. And don't forget, I have to click and drag all the way down. Click and drag. Okay? When you have subsonic speeds, we do not have this constructive interference right here at the region of high pressure. Okay? That's why we see that, we hear that sonic boom. Higher pressure means louder sound. And if going back to what we had before, right, here you go. Here you go. Let's animate it. Let's animate it again. Here you go. Supersonic speed is actually Mach equal to 1. The source is moving with the crest of the wave. When it comes at the point where the period is equal, the time is equal to the period of wave, we have a second wave front coming out, and the front of the second wave front overlaps with the front of the first wave front. Okay, at time at instant of time equal to the two periods, we have a third wave front emitted here, and then we have a third constructive interference, tripling the original pressure there at the front of the wave. Okay, let me see one more coming. Okay. And then what we have here an angle that's perpendicular to the path of the aircraft. That's for Mach equal to 1. Okay, velocity of the source is equal to the velocity of the wave. By the way, this type of phenomenon we notice it not only in supersonic aircraft, but also with boats, okay? When boats are moving in the water at speed greater than the wave, than the water wave, they also form this type of path in the water. Have you seen that? Path in which the boat leaves a triangular wake. That's because the boat is moving at speed faster than the wave itself. And then, that's what I'm going to show to you right now. 1.5. What I mean 1.5 is actually 1.5 the speed of the wave, not necessarily the speed of the sound, okay? Here you go. And then I have to change everything else. Here should be 15. And this other one should be 15 as well. Is that 15? No, it's 30. Okay, let's go click and drag. Okay, and this one should click and drag as well. Okay, now let's start again. 0, right? 1, 2, 1, 2, 3, 4, 5, 6. See that airplane leaving the wave front behind? Because it's flying faster or moving faster than the wave itself. 9, 10. Here you go. At this very moment is going to emit another wave. Here you go. And here's the wave. 11, 12, 13, 14, 15. Okay. And then we have this cone leaving behind the airplane. Okay, here you go, the cone that you see. And then let's keep on going. 15, 16, 17. Now I'm running out of space for the other wave. The source is going to, what do we have? 16, 19, let's see, 20. We should have another wave now. Yeah, but we run out of space in our graph, right? Here you go. 22, 20, oh, 22, here you go, 23. Okay, so from this pattern, from this line that you see here connecting, you know, if you connect the source to those lines, we form a cone that has a given angle. And this angle of the cone can be used to determine the speed of the source. Okay, so how do we do that? Supersonic speed, not this one. It's this one right here. And here we have another drawing. We did that, right? Okay, shock wave. Okay, this pressure wave makes an angle of 90 degrees with the path of the projectile, okay? So when the velocity of the source is equal to the velocity of, that's the relationship that you get. That angle that you saw, sine of theta, is going to be equal to V over Vs, okay? Velocity of the source, velocity of the wave. If the velocity of the source is 1.5, here you go, is 1.5. So the sine of the angle is going to be 1 divided by 1.5. And that's here you go. Here's the source. So this line here, this angle theta, let's connect the source to a direction that's tangent to the front of the wave. Okay. So here you go, theta. That's the velocity of the wave times t. That's the velocity of the source times t. Right? Velocity of the wave times t times divided by velocity of the source times t is equal to the sine of theta. That's where I get that relation that you saw. And that's what we have for this section here. Okay, do you have any questions about that? Let me see if I can find some real life examples of supersonic speeds. There's some pictures. Okay, that's the case. That's not exactly what I want, but that's the region of high pressure, right? But let's see here. NASA has some really interesting pictures that shows this cone clearly. Real life type of pictures, supersonic flight. Let's see if we have it here. And oh yeah, here you go. Do you see the shock wave right in here? Here's the projectile, okay? The shock wave being formed. If you measure this angle right here, you can determine what the speed of this bullet. Okay, bullet fire from a gun travel at supersonic speeds. This case is 1.5 times the speed of the sound. So this sine of theta here is 1 divided by 1.5. That's a real picture. Okay, and the faster you go, the steeper this angle is. Okay, forming a region of high pressure. That's why we hear the sonic boom. Okay. The noise is called a fast release of air. Sonic boom is a loud noise like thunder. Apparently, you'll never hear a sonic boom when an aircraft flies overhead at supersonic speed. The noise is caused by a fast release of air pressure. Okay, air pressure builds up as the plane flies through the air. When the pressure is released, it makes a loud noise. This is similar to when a balloon pops. Okay, so it's the change in pressure, right? It's the change in pressure that we end up having. So it's 11:23 right now. Let's see, someone is bullets. Depend on the bullet, depend on the gun, right? Some bullets go hypersonic, yes, but it's not every gun that can fire a bullet with speed that hypersonic. Yeah. Okay, they depend. You know, it all depends on the gun itself, how fast it can fire the bullet. But there are guns out there that can propel bullets at supersonic speeds. Okay. So it's 11:23 right now. The exam, I put it to I scheduled the exam to start 11:59, 1 minute before 12 noon. So you're gonna have 1 minute more, okay? And I'll be monitoring you. Don't forget to turn on our webcam. Make sure you have a reliable internet connection there. If you don't turn your webcam, I'm gonna block you out from the exam. So make sure you have your webcam turned on all the time so I can monitor you, okay? So let me stop recording right now. I will